Hi, let us understand how unstructured data will be handled within machine learning. For understanding purpose, let us assume I do have an image of 3 cross 3 pixel. So let's assume this is an image of size 3 cross 3 pixel. And each pixel will have an RGB value, red, green and blue. It will have an RGB value. For understanding purpose, let's assume the RGB value have been merged together to represent a number. So for each pixel, based on the color, what color it is, I'll be having some number attached to it. Now, I have a mechanism to represent each pixel as a number. What I'll be doing, I'll be reading these pixels in some order so that it can be converted into a vector. So these 9 pixels have been represented as a vector with 9 dimensions. Like this, let me assume I do have another image. So that image will also have some numbers and I can represent that as a vector. And we have assumed lots of assumptions like both the images are of same dimensions as well as and each image, each pixel can be represented as a number. But practically each image could be represented as an RGB value, the contrast and different items. Now let's leave that apart and that would be handled by the machine learning algorithms. For understanding purpose, I do have two vectors with 9 dimensions. I can find the distance between these two vectors. Now, if I bring in another image, what I can do, I can find the distance between them and that would help me or facilitate me to identify whether those images are nearby or not, or in the sense whether the image is related or not, I should be in a position to identify. So this is how we will be converting the data or the unstructured data into some vector form and take it for further calculation. Now you may be wondering, am I going to do all such complex calculations for each and every image? No, there are some built-in algorithms. Let me represent that with a mathematical form. Let me assume I do have n number of data points within an image. Let's consider that as a two-dimensional data space. Let me say I'm going to have n number of data points. Let me assume these are all the data points. The same way, I do have another image. For another image, let's say it's having its own data points. So for the second image, these are all the data points. Now, I can represent the first image as a function. Since it's a two-dimensional space, I can represent that with a line. And all these data points, it's going to have a small variation from the function, the pluses and minus. So what that is, I am going to represent that. So this much amount of deviation from this particular function each data point has. The same way, the other image can be represented by another data point, something like this. This particular image will also have some deviation from this particular function, and what that is I can represent. But overall, if I superimpose these images one after the other, something like this is where the real understanding is going to come into picture. I can find a common function between these two data points. The green and the blue, I can find some common features. If you see, there are some overlapping between these two data points. What I can do, I can extract only the common features out of it. So I'll be having a common feature. And the image 1 is the common feature plus delta 1. And the image 2 is common feature plus or minus some delta 2. The delta could be a function. It could be a complex function. All I need to represent is what is the common feature plus what is the variation from this particular common feature, something like this. I can represent that by a function. I can demonstrate that with the eigen images. If I have n number of images, let us assume I have n number of human faces. With all the human faces, there will be some sort of a similarity. What I'll be doing, I'll be extracting those common features, the common element. For example, this particular image, the second image, I should be in a position to correlate with all the images that I have. So if I bring in a new image into this particular eigen face, against each of this particular image, how much delta or how much variation the image that I have brought in is having. So this type of calculation, we call it as dimensionality reduction. So what I have done, rather than representing each and every image, what I will do, if I have 1 million images, assume I have 1 million images, I will be extracting the eigenfaces, that is the common face across all this, and each of this particular image that I have, I'll be representing that as a delta. So the dimension of it will get reduced, d1. So the common face plus the d1 is what going to make the difference. Now I will try to find the difference between these or compare these images, and comparison is going to be much easier and faster. So what I have done, rather than looking into the entire picture as it is, I am just moving away or taking away all the common features out of it, and I am going to look at only the features that is going to make the differentiation within that particular image for my calculation purpose. This is where the dimensionality reduction plays a significant role, especially on the unstructured data. And let me prove it with another example. Let me explain this with another scenario. Let's assume I do have two tweets. The first tweet, it's talking about some technology, and I do have another tweet. What I'll be doing, each of this tweet, I'll be calculating how many unique words I do have and their count. So I'll say I do have a word called Apache once, distributed thrice, computing thrice is 2 times, and so on. The same way, I will be doing the word frequency count for another tweet. For this particular tweet, I do have distributed as 3, computing as 3, and maybe is as 2, also 1, processing 1, and so on. What I will be doing, I'll consider each and every word as a dimension. Observe very carefully. I'll be considering each and every word as a dimension. So if I do have a word something like this, say computing, Apache, processing, so I will collect all the unique words across these two tweets. So I do have Apache, distributed, computing is, and processing. So distributed. Let me represent this in the vector form. I do have computing as 3 and Apache as 1. So processing is 0 and distributed as 3. The second vector, the second tweet, I'll be representing over here as computing is 3 times, Apache is once, processing is 1, and distributed is thrice. So what I have done, I have represented the first tweet in a vector form for each of this word. I don't have the processing word in the first tweet, so I'll represent that as a 0. And I don't have the other words, and I do have all these 4 words. So what I'll be doing, I will consider what are all the terminologies that's going to make relevance. For example, I can ignore all the words like is, was. There are some ways available within the data science like term frequency, inverse term frequency. Let's not worry about that. That would facilitate to remove all the common words that is appearing in all the common tweets. Very simple example, we call it as a stop words like is, was. That's not going to make any significant importance to that particular tweet. So I'll consider only the features or the words that's going to make a significant impact on that particular tweet. I'll consider only those words and their count, and I'll consider all the words across the tweet. I'll consider that as a dimension. So here, for example, I have considered as a 4-dimensional space, and each of this dimension, how many counts are available, and I should be in a position to represent that as a vector. Once the vector is available, I can find the distance, I can find the correlation, and that's where we are going to identify all the tweets where it is having a spam words, or all the emails where it is having spam or non-spam emails. I should be in a position to segregate. So we have seen how I am going to use the dimensionality reduction as well as the way of representing any unstructured data in a computing world, so that I can leverage that with the machine learning to do the similarity.